Hi guys, so let's talk about section 11.2 part 1, inference for relationships. Okay, so we did in last section 11.1, we did chi-square goodness of fit test. Okay, today we're going to do something quite different. If you remember, the chi-square goodness of fit test was one sample, and then we looked in that sample how is a specific categorical variable distributed. For us, the first example we did was color, and then we had a bunch of colors, and we were testing to see if they were distributed according to a claim from the Mars company. Okay, that's chi-square goodness of fit test. A single sample, okay, and a single categorical variable, and we check a claim about the distribution of that categorical variable for a single sample. Today we want to talk about a different test, very, very different test, and this is called chi-square test for homogeneity. So if you look in your resources folder for chapter 11, and you look in the student note sheet folder, you'll see that I added this page there, and I think what it's called is it's called distinguishing between chi-square tests. Oh, it's exactly this. This is what it's called in the folder. Okay, and the reason I made this is not in your textbook anywhere, but the reason I made this graphic for you is literally to help you distinguish chi-square tests, because students have a hard time doing that, and the textbook tries to explain this verbally, but I think a visual is a little bit more helpful for you. So I created this for you. You can see my wonderful graphical design skills at work. Any case, this was section 11.1. Okay, chi-square goodness of fit test. This is section 11.2 part 1, which is a chi-square test for homogeneity, which we're talking about today. And the principle here is different from goodness of fit test. For goodness of fit test is one sample. For test for homogeneity, we're comparing the distribution of still a single categorical variable, still just one categorical variable, but we're comparing the distribution of that categorical variable across many samples. Okay? It doesn't just have to be one. So this is what makes this different from a chi-square goodness of fit test, is that I'm checking the distribution of a categorical variable across multiple samples or multiple treatment groups. Okay, you can actually add their treatment groups, which is actually our first example. So hopefully this is useful for you to distinguish the two. If there's multiple samples, it's definitely a test for homogeneity. You'll see next time we talk about test for association, there's also only one sample. So if you can clearly tell that the chi-square test, the prompt you're given, involves multiple samples or multiple treatment groups, then you're doing a test for homogeneity. Okay? And again, so our claim actually will be that this categorical variable is distributed the same across all these populations. So I want to be doing a test to see that this distribution here, this proportion is the same as this, is the same as this, and then this one is the same as this one, is the same as this one. That's our claim, that there's no difference in the distribution for all of these, for this one categorical variable across the samples. Okay, so that will be our null hypothesis that we're going to work towards. Unfortunately for you, we have some review to do and some, well, maybe it's fortunately for you actually, we're going to do some review about categorical variables and distributions for our first example. But that's the gist. So let's go back here. That's the gist of what we're trying to do today. I'll let you read this. You can read that if you want. Good for you. Let's just dive in and do the example, okay? And so it says, market researchers suspect that background music may affect the mood and buying behavior of customers. One study in a European restaurant compared 3 randomly assigned treatments. Okay, So 3 assigned treatments. All right, and here are the treatments. No music, French accordion music, and Italian string music. And I usually in class, when we're together, I look this up with the students and we listen to some of it. It's very interesting. I mean, Italian string music, you know very well. You know, it's some of the great composers that we listen to. French accordion music is an entirely different beast, and you probably do know what an accordion is, but it sounds completely different. It's very interesting. And then no music. Okay, so dining in silence, that's the third treatment. All right, so here are the 3 treatments. 3 treatments, and then 3 treatment groups. So in each group, there were this many entrees ordered for each group. Okay? All right. Under each condition, the researchers recorded the number of customers who ordered French, Italian, and other entrees. So again, entree ordered. I'm going to draw the picture equivalent to this picture so that you get the idea. Okay, the picture that's equivalent to this picture. And so what we have there is this. Okay, entree ordered, and then we have French, Italian, and other. Okay, these are the values of the categorical variable entree ordered. And then I have my 3 treatment groups, or 3 samples is what the note sheet said. So here are my 3 treatment groups. Okay, none, no music, French music, and this is music. Okay, and then Italian music. Now, this is not a categorical variable distributed across samples. That's not what this is. These are 3 treatment groups. Okay, it could be 3 samples, but these are 3 treatment groups. And so we can say music treatment groups. Oh, and sorry, by the way, you don't have to write this down on your note sheet. I'm just doing a bit of a comparison for you so you can see how this goes with the graphic I gave you. Okay, and now our test that we're going to want to do eventually after we do the review stuff is French, well, are French entrees distributed the same across each treatment group, and then are Italian entrees distributed the same across each treatment group, and are other entrees distributed the same across each treatment group. So we want to see if these distributions are all the same. That's what we're testing. Okay, that's what we're testing. And if they're not, that tells us something, that one entree is preferred over the others or something like that. And we can say specifically when, and you'll see that a little bit towards the end of this marathon note sheet. Okay, so that was not really the question. That was just the setup that I want you to understand the big picture. So the question here is something very different. This is a throwback to chapter 1, which most students actually had a hard time with, and that's conditional distributions. Most students had a hard time with this. So here's the question. Calculate conditional distributions for of entrees ordered for each treatment. Okay? Calculate conditional distribution of entrees ordered for each treatment. So, for each treatment, here's a treatment. I want to calculate a conditional distribution by entrees ordered. Okay? So for each treatment, I want to calculate a conditional distribution. And how that works is this again. Okay? You say, okay, for the no music treatment, what proportion of the entrees were French? So there were 30 out of 84. Okay? And that's how you calculate the conditional distributions. So you would do something like this and say, calculate the conditional distributions, no music, okay? For that specific treatment group, when no music was playing, the conditional distribution of French entrees was 30 out of the total 84 entrees ordered when no music was playing. All right, and that is 0.357. In a proportion, that means this. Okay, actually both of those are fine. All right, and then so on and so forth. So Italian, the distribution of Italian entrees for the treatment group of no music playing is 11 out of 84. 11 out of 84, and that gives me about 0.131. And then for other, how many other entrees, or what proportion of other entrees were purchased when no music was playing, and you do 43 out of 84, and that gives me about 0.512. So this is one conditional distribution of entrees for no music treatment. Okay, this is one conditional distribution. This whole thing is one conditional distribution. So you have to do that for all three, because there were three treatments. So you have to do all three. So then you do French. Okay, French music, I guess, sorry, because there's French entrees too, that's confusing. And then you will do French music, French entree, French music, Italian entree, and French music, other entree. Okay, and then you just do the same thing. At this point, it becomes repetitive. I don't want to do all of this with you because this is going to take too long, I think. At this point, it's just, again, the conditional distribution of entrees for this treatment would be 39 over 75, 1 over 75, and 35 over 75. And so when you do those, let me write one more. Okay, I'll do this, and you get 0.52. And then the other ones, if you keep doing the same thing, 1 over 75, you get 0.013, and then this one you get 0.476, and so on. And so Italian, I'll let you do that one by yourself. Okay? So these are conditional distributions. So all you really have to write down is this. All right, those are your conditional distributions. And actually, you can also just list them as a table. So this is the work you would do, but you could also actually just list them as a table and just write this exact table, except you can leave these columns out, and then you can just literally list 0.357, 0.131, and 0.512, something like this. All of these will add up to 1 and 1 here. Okay, so any case, that's the conditional distribution. Review from chapter 1. Right? Remember, just for interest's sake, I don't know if you remember this, but marginal distributions. What are marginal distributions? That is this one, 84 over 243, or 75 over 243, or 84. Those are marginal distributions. Interesting if you remember that. Okay, make a bar graph. So what you would do here, you have 3 distinct conditional distributions. So what I would do is just make 3 distinct bar graphs, if I were you. Okay, and this is not really too difficult. Just remember, when you make a bar graph for AP statistics, it has to have consistent scale and labels, all those kind of things. All right. So what we want to do is do something like this: bar graph. Bars don't touch. Okay, bar graph. Bars don't touch. It's not a histogram. And then you would put your labels. So right here I would put, let's say, my entree, and right here I would put proportion or percent. It's really up to you. Okay, I think let's do percent. That's a bit easier to read. Percent goes here, and then we can do a graph for the conditional distribution. So what I need to do is write down my 3 entrees at the bottom: French, Italian, and other. So I have to do French, Italian, and other. And then just write them down as percentages. So this would be like 36%. Okay. Now let's make a consistent scale. My biggest percent I'm going to have is 51%. So maybe go to 60%. So like 10, 20, 30, 40, 50, 60, something like that. Okay. And then just make your bars for your bar graph. And so for French, I have 36%, about just over halfway here. And then for Italian, I have about 13%, so just over 10, something like this. And for other, I have 51.2%, so just above 50, something like this. Okay, and then you do the same for French and Italian. I don't want to go do all that. I think making a bar graph is something that you're better at than I am, so I don't really need to show you all that. All right, and then write a few sentences comparing distributions. All right, so I'll let you look at that. You can write some sentences comparing the distributions. You can check out the completed note sheet. Basically, you'll see some trend and you'll comment on the trend. Okay, and this is not a big deal. It's fairly straightforward. What we really want to get into is not to review stuff, but we want to get into the actual hypothesis testing. Okay, so let's look at this together here. It says the researchers in the restaurant study expected that music would influence customer orders. So their expectation is that the distributions of the categorical variable across all the treatments are not the same. That's actually what they want, to prove that the type of music you're playing makes people buy a particular entree more often. That's what they're hoping to show. Okay? But the null hypothesis would be that there is no difference, so that the music makes no difference, basically. So a good general strategy is to compare the conditional distributions of the response variable for each of the explanatory variable. That's why we compared conditional distributions of entrees for each type of music. It's common practice to describe a two-way table by its number of rows and columns. Okay, and so for instance, this was a 3x3 table, of course. Here's the data, 3x3 table. These are totals, but not actually data. These are the actual data. Okay, okay. And then hypotheses. How do I state hypotheses for this type of a test? Very difficult to state it with like subscripts and this proportion and that proportion. So this is an easy way, and this is what you want to do for this type of chi-square test. You don't want to try and do the first or second approach we talked about for goodness of fit. You just want to write it this way. Okay? There's no difference in the distribution of entree orders at this restaurant when no music, French accordion music, or Italian string music is played. Or there is a difference in the distribution of entrees ordered at this restaurant when no music, French accordion music, or Italian string music is played. So, if the null hypothesis is true, there's no difference. The observed differences for the three groups are just due to chance. Okay? The alternative hypothesis says there is a difference, but we don't know what that difference is. Okay, and this is where something called follow-up analysis would come in, and we'll talk about that a little bit. So, the alternative hypothesis here, there is a difference in the distributions, is not one-sided or two-sided. Okay, you might call it many-sided because there's many different options. It's not just they're not equal to or one is less than or greater than. It's that there's a whole bunch of different things that can happen. Okay, and so if you want to use the kinds of tests we've done in the past for proportions, because we're talking about proportions, you'd have to do many different tests, like do a hypothesis test for this proportion and do a hypothesis test for this proportion, for each proportion, for each treatment separately, like 9 different hypothesis tests or something. Okay, but that's a bad idea. That's still not good, because when you do that, you are separating the data from each other, and you're not taking everything into account together. So we want to do all the inferences taken together. If you pick out some and then do a test about some of the proportions, that's not really a fair test or a fair comparison anymore. So if you want to talk about all of these things together, you need to do a test that takes all of it into account together. Okay, and so this is called the idea of multiple comparisons. So we're comparing essentially, 9 different things, three proportions for 3 different treatments. And so how this normally works is you do an overall test, which we're going to do together, hypothesis test, and then afterwards you will do a follow-up analysis to see which of the parameters differ the most usually. You'd look at which ones differ the most and go, ooh, something is happening here. So maybe this particular music is influencing people more than this other type of music. So maybe I should play this particular music if I want to sell these particular types of entrees or something like that. Okay, so we'll see that in a second. So the overall test is not very different from anything we've done for section 11.1, except that the data is different, so your actual way to calculate your expected counts and things like that are quite different. Okay, so chi-square test for homogeneity is what we're talking about here, because there are several populations or treatments. In our example, there are 3 treatments. If there's 3 treatments or 3 samples or multiple samples or multiple treatments, it's not goodness of fit test. Now it's a test for homogeneity. Okay? And this is how you write your null hypothesis in general, and this is how you write your alternative hypothesis in general. Okay? So, the null hypothesis, in the restaurant experiment, there's no difference in the distributions of the entrees when no music, French accordion music, or Italian music is played. To find the expected counts, we start by this assumption. Okay, so remember, a hypothesis test is usually a statement. The null hypothesis is a statement of no difference. There it is again, statement of no difference. So if you think about that, then what we're about to do makes sense. If you don't have that in mind, then this becomes really weird. Okay, how do you calculate the expected counts? So here are my observed counts. How do I calculate my expected counts? So we are saying the null hypothesis is true. We're assuming that in our null hypothesis. So that means that the distribution of the entrees for the treatment is the same. So that means this. If I'm looking at the French entree, the distribution of the entrees must be the same, proportionally speaking, for each treatment. Okay? So what is the distribution of the entrees compared to the total entrees? So there were 99 French entrees ordered, and there were total 243 entrees. So I can get this proportion of the total. Okay? So that's the proportion of the total. All right? Okay, so I just do this. I say, let's talk about French entrees first. Okay? And let's talk about finding the expected counts for French entrees. All right? So I'm going to write French entrees. Okay? And then we do the distribution. So what would I expect to find for my counts for none? Okay, for the treatment none. So it should be 99 out of 243. But the problem is that the number of entrees ordered is different in each treatment. So I can't just write 99 over 243 everywhere. Okay, this is what we want to do. And it's almost what we do. But I can't do this because that's not legitimate, because I have to do 99 out of 243 of the entrees that were ordered in that treatment group. Okay? So can't do this, but that's close. So for none, when no music was playing, let me write no music. Maybe that'll be clearer for you. So when no music was playing, which they're calling none, okay, what is my expected count? So my proportion is the same. I'm assuming this, that's true. I'm assuming that the distribution is the same. That's my null hypothesis. The distribution is the same. So I'm assuming 99 out of 243, okay, for when no music is playing. I'm also assuming that same thing when French music is playing. And I'm also assuming that same thing when Italian music's playing. Okay? 99 out of 243. But I have to do that proportion according to the number of entrees. Otherwise, when I add up all my expected counts, I might exceed 84 or 75 or 84, which that can't happen. I have to keep my expected counts proportional to the number of entrees that were ordered in each treatment group. Okay, so I have to say here, I can't do this, and let me erase all my scratch here. Okay, I can't do this, so what I'm going to do is say, for French, it's 99 out of the 243, okay, but times the total number of entrees in the French treatment group, okay? So I'm going to do here times 84, okay, which is the total number of, oh, sorry, I said French treatment group, the non-treatment group, the total number of entrees in the non-treatment group, okay? And then for French, I want to do 99 out of 243. It's the same proportion. We are keeping the null hypothesis, but times the number of entrees in the French treatment group. Okay, so this would be times 75. And then here, still same proportion. We are doing that times the total number of entrees for the Italian treatment group. Okay, so 84. And of course, then the first and the third one must be the same. You get 34.22. Don't round that, just leave it 34.22. This is 30.56, and this one would be 34.22 again. Okay? And that's that. So what we actually have, and you don't have to write this stuff down, okay, that's just the work. What we actually have then is 34.22, 30.56, and 34.22, since they had the same total number of entrees ordered. Okay, and then you do the same thing for the next type of entrees. So we did French, then we can do Italian. Okay, and if you do Italian entrees, again, what's the proportion of Italian entrees of the total? 31 over 243. So I go, for each treatment group, no music, French music, and Italian music. I need to come up with all my expected counts, okay? So I start with my expected proportion, which is 31 out of 243, 31 out of 243, and then I would do times the total number of entrees in the no music treatment group, which is 84. And that gives me 10.72, okay? And then 31 out of 243 times 75 again, and that gives me 9.57. And then 31 out of 243 times 84 again. Okay, and that gives me 10.72. So you can see what we're doing here is preserving the size of the total orders proportionally. Okay, but we are, just remember this, we are assuming that the distribution is the same across all the treatments. Okay, we are doing that, but we're just scaling it proportionally to how many entrees were ordered in each treatment. So I think this is pretty clear. It's a bit weird in the beginning, but I think it's pretty clear. And so what you get is this, and then if you do other, I'll just put the numbers in because I've already done all the work. I want to write everything out again. 39.06, 34.88, and 39.06. Okay? Now, you may think to yourself, I never want to do a hypothesis test of this type in my life. Chi-square test for homogeneity. Let's run for the hills. So, The idea here is that you understand the concept of how these things get calculated. Good news for you is you're never going to have to do this by hand again. Okay, we did it by hand once so that you understand the concept of how this works and that you see the null hypothesis true assumption at work, but that's it. Okay, we're not going to ask you to do this again. Fortunately, your calculator can calculate all of this for you. So just like we saw it for the goodness of fit test, you got the contributions or components of the chi-square statistic calculated for you. Your calculator can do all this. Okay, but I'll do that test separately. So we're going to just proceed here as if we would normally proceed, assuming we calculate everything by hand. Okay, so here is the general rule for calculating expected counts. So if you understand this concept, I don't think you really need the formula, but okay, here's it is, okay? It's the row total divided by table total times the column total. So we wrote it like this, row total over table total, which is the null hypothesis proportion basically, and then we multiplied that by the column total. Okay, same thing, no difference there. All right. This is not on your formula sheet, not on the formula sheet, okay? Any case, you might not need to know this because your calculator will do it for you if you don't remember. All right? And then conditions for performing a chi-square test for homogeneity, same. Same as the conditions for performing a chi-square test for goodness of fit. The conditions are the same, okay? No difference there. And yeah, nothing else to say. So we did it. We did all our expected counts, observed counts. So here's the question. The tables below shows our work, and then it says calculate the chi-square statistic. Okay. So calculate the chi-square statistic, show your work. So again, we said this is on the formula sheet. Chi squared equals the sum of observed minus expected squared over expected. Okay, and then we just full stuff in. Now here's 9 things to do. We are not doing 9 things. You can forget that. Okay, so what we do is our strategy. We write your first observed count minus my first expected count, 34.22, squared over my expected count, 34.22, plus, let's do another one. So let's say we proceed from left to right in the top row. So we do 39 minus 30.566, 30.56 squared over 30.56 plus, and then do some ellipses and do maybe the last one, okay? So the last one would be 35 if I proceeded from left to right, and then top to bottom, 39.06 squared over 39.06, okay? This is totally sufficient to show people what's going on. And then you say, okay, chi squared is, and you can, unfortunately, for you to do the components here, you have to calculate them by hand. The components are not something that the calculator does for you. I think if you have a TI-89, it does do it for you. But a TI-84, we don't get the components, okay? So to calculate these things, you have to do them by hand. And if they want to ask you anything about follow-up analysis or something, which it's unlikely they'll do, they might just give you all the stuff and say, talk about what might be going on here, but you have to calculate this by hand. So you literally just want to enter this thing in your calculator and get 0.52 plus, and then do this one in your calculator and you get 2.33 plus plus, and then the last one, if you do that, you get 0.42. Okay, I haven't played with this too much, but I think you need to calculate this by hand. I don't know if a TI-84 does this for you. All right, and then finally you get chi square is 18.28 Chabourdot. All right, now we're going to show you how to do this on your calculator. I'll make a separate video for you to show you how to do this on your calculator, and it's beautiful. It goes from your observed counts, gives you the expected counts, and gives you this, and so life is good. Okay, it's not that difficult. Like I said, I think the only thing you might have to do a little bit manually by hand is to show those three numbers. Okay. So it says AP exam in the do step you aren't required to show every term. Oh, guess what? We just did that. All right. All right. So you know how to do this, and actually, technically, you know how to do the p-value too, because the p-value is just this question. What's the probability that chi-square is greater or equals to 18.28? And you find the p-value. You can do that using chi-square CDF. You know how to do that on your calculator. And remember again, chi-square is the smallest number you can have is 0. It's a heavily right-skewed distribution depending on how many degrees of freedom. And then you put your chi-square statistic here, and we're looking for this area here. Okay, so chi-square test for homogeneity. So we use the chi-square goodness of fit test. Test hypothesis model for distribution of one categorical variable. Great, we just said this. If we want to work with several populations or treatment groups, we do chi-square test for homogeneity. Okay. Now here's the thing we did not talk about to calculate this p-value. Remember we said you have to list degrees of freedom. What is the degrees of freedom? Okay, or what are the degrees of freedom? So in this case, degrees of freedom are this. Number of rows minus 1 times number of columns minus 1. So for ours, we had 3 rows and 3 columns. So 3 minus 1 times 3 minus 1. Okay, so our degrees of freedom should be 4. All right, so again, state your hypotheses, plan, check conditions, do. There you go. Life is good. So there we are. Here is our example. We've been cranking along all along. Okay, and here's the chi-square statistic we had. Find the p-value. So do the test on your calculator. I'll show you how to do that in a second. But you're basically calculating this. What's the probability that chi-square is greater or equals to 18.28? And the chi-square CDF, if you do it that way, I'm going to write it down. Please never write this down anywhere, okay? But I'm just writing it down since we're using TI-84. You would do, that's your lower, your upper bound, go 10,000 is always a good one. And it asks for degrees of freedom. So degrees of freedom for us is 3 minus 1 times 3 minus 1, which is 2 times 2, which is 4. Okay? Because we had 3 categories, 3 entrees, 3 different types of music were the treatments. So 4, and then you get your chi-square statistic, your p-value, sorry, of 0.011. 0.0011. All right, and then what conclusion would you draw? Okay, justify your answer. What conclusion would you draw? So you would say, since the p-value, which is 0.0011, is less than an alpha of 0.05, we reject the null hypothesis. Okay, so in this case, what were we talking about? We reject this. We have evidence for this. Okay, we have sufficient evidence to conclude. We have sufficient evidence to conclude that what? There is a difference in the distributions of entrees ordered distributions of entrees ordered at this store or at this restaurant for the 3 different music treatments, okay, or types of music. Okay. And now, that doesn't maybe seem too astounding or important or great of a result. So what, right? And that's where the follow-up analysis comes in. So this is a very powerful result. You are saying that, look, it doesn't not make a difference what music I play. This gives you the result saying it makes a difference which music I play, okay? According to which entree people order. So then we have something called the follow-up analysis. So we just did the test. This was the first part of the multiple comparisons thing we were talking about earlier. We did the hypothesis test. We got a strong conclusion. Okay, now that we know there's definitely a difference in the distributions, well, there's very likely to be an actual difference. We're still talking probability here. Then we can do follow-up analysis. And what you want to do in follow-up analysis, so please, students get really confused with this in their homework. And I don't know if they get confused with this on the test, but in the homework there's questions. They're like, what am I doing with follow-up analysis? My life is falling apart. Help me, okay? It's not that bad, okay? So we're comparing a whole bunch of different treatments and a whole bunch of different categorical variable values, okay? And so here is a table of what we found. So let me just take you back a little bit. This is to understand what this means. These were my observed counts, okay? These were my expected counts, and these were the contributions or components of the chi-square statistic, okay? So if we go back up here, remember, my observed count, my expected count, and that together led to this contribution or component of my chi-square statistic. So that's what this table is showing, okay? And so what we look at for follow-up analysis are these numbers, all right? We want to see which things contributed the most to the chi-square statistic. Those are the things that are having the most influence on the chi-square statistic, and those are the things that likely have the biggest difference between observed and expected. So those are the things I have to do more investigation in, okay? And so this is a huge contributor. The whole chi-square statistic is 18, and those two combined are 14, okay? So 14 of the 18 points towards the chi-square statistic are those two categories, or is this one category in the two treatments? And so what is this category? So this was what? We have to go back to our data and look, okay? French, Italian, other. So this was French, Italian entree, and other entree, okay? So what we're saying is the biggest difference I saw, or the biggest impact, was French music playing on the number of Italian orders, and Italian music playing on the number of Italian orders, okay? So now you can see what's happening here. This is my observed count. When French music was playing, I observed way less Italian orders compared to what I expected, okay? So again, this is my observed, and this is my expected. So that's why this is so big. There's a huge difference between these two numbers. You can look at the other ones, they're all fairly close. Not too bad, okay? And then the other way to interpret this is what I observed, the number of Italian entrees that were ordered when Italian music was playing, was way more than what I expected. Okay, so that's the follow-up analysis you would do. You would write something about that. Okay, and so that's all they're talking about. It's not a big deal. You identify the bigger numbers, the biggest numbers, and you talk about interpreting what does that mean. Okay, what does that mean? So when French music was playing, there were a lot less Italian entree orders than what we expected. Okay, this number is less than what we expected. And when Italian music was playing, there were a lot more Italian orders than what I expected. Okay, and that's it. That's the follow-up analysis. Now, if you're a real statistician, you would then go and do some other hypothesis testing or experiments or whatever to see how you can milk this situation, okay, to help the restaurant make more money or something. Maybe change their menu or something, okay? All right, so that's the follow-up analysis. All right. And we don't do this, okay? More advanced methods provide tests and confidence intervals that do more. We don't do anything like that. Not in this class, okay? So, example 5, and then we're out of here. Ho-ho. Thank you. Example 5, okay? So let's do example 5. Example 5 said, random digit dialing telephone surveys used to exclude cell phone numbers. If the opinions of people who have only cell phone numbers or cell phones differ from those who have landline service, the poll results may not represent the entire adult population. The Pew Research Center interviewed separate random samples of cell-only and landline telephone users who were less than 30 years old. So here's the key for you to know what to do here. Separate random samples. Okay? When you see a table of data like this with separate random samples, you're talking chi-squared test for homogeneity. Okay? For homogeneity. All right. When you see that, separate samples, and there's two categorical variables. One categorical variable, but two separate samples. Okay. Here's what the Pew survey found about these people described their political party affiliation. So what we have here is the categorical variable is political party affiliate. Am I writing that correctly? Affiliation. Okay. That's my categorical variable, and it has these 3 categories, okay? And here are my 2 samples, sample 1, sample 2, all right? So, do these data provide convincing evidence the distribution of party affiliation differs in the cell-only and landline user populations? Carry out a significance test. All righty then. Let's crank through that whole thing, okay? So, state, we will perform or conduct a test of the following hypotheses. Null hypothesis. So what's our null hypothesis? Do the data provide convincing evidence the distribution of party affiliation differs? Okay, so there is no difference, okay? There is no difference in the distributions of party affiliation between cell-only and landline populations, okay? Between the cell-only and landline populations. All right? And then my alternative hypothesis would be there is a difference in the Okay? Please, I don't want to write all that out. You have to write all that out on a test or in your homework, something like this, but I'm not going to do all that. And then we just say, as we usually do, state your significance level, and they said alpha is 0.05. Technically, you don't have to do it if they tell you what to use, but okay, I'm just going to keep going with what we've been doing. Okay? And then state, that's fine, then plan. So, if conditions are met, we'll perform a we will perform or conduct, what do we say, perform, we'll perform a chi-squared test for homogeneity. For homogeneity. Okay? Now, I have to say something to you guys. I don't want to say this, but I'm going to say it to help you on your AP exam. If you forget which test you're busy doing and you're completely lost, then just write, I'm going to do a chi-square test. Okay? So if you forget how to distinguish between chi-square test for homogeneity or test for association or something like that, you just write chi-square test. Okay? Because the math is fairly similar. If you're using the data correctly, the math is not that much different for these two tests. So, in any case, if you forget this completely, then you could do that. You'll see that when we do the second part of section 11.2. All right, so there's that, and then random. So data come from separate random samples. Okay, the data comes from separate random samples. Okay, from separate random samples. All right, and then large counts, and remember, large counts refers to expected counts. Okay, and so then we do expected counts. And you have to go into your calculator and do the hypothesis test. Okay, do the chi-square test on your calculator. All right. So I'm not going to show you how to do that right here because I can't do that on my iPad and my computer wants to explode when I do that. So do the test on your calculator and you'll see this. The expected counts are all greater than 5, and it's not enough to just say that. You have to list them. You have to list them. So you're going into your matrix B and you're finding the expected counts. Okay, and when you do that, you get 46.08. And again, here you're going to have what? 6 expected counts. Okay, 49.92, 20.16. 21.84, 29.76, and 32.24. Okay, so you say the large counts condition is met, or the sampling distribution of the chi-square statistic will follow approximately a chi-square distribution. Okay. I would highly recommend you just write that. That's easier. Okay, and then independence. What are we talking about? Samples. So we're talking about what? 96 and 104. So we have to say. We have to assume that there are more than 960 and 10,400. What? Cell phone and landline users. Okay. What's the first one? First one is cell only. Okay, cell only and landline users in their respective populations. Okay, and then they're separate random samples, so the samples themselves should be independent. Okay, so these people within the sample should be independent, and then the samples themselves should be independent. Okay, and then do chi-squared is, again, I would write the whole formula if I were you, because that's how good you is. observed minus expected squared over expected, and that's equal to, and you write some stuff out. Don't write everything. Do the test on your calculator first, find your expected counts. So 49 minus 46.08 squared over 46.08 plus, maybe do another one on the front end. So what are we doing? 47 minus 49.92 squared over 49.92 plus plus, in the end, 30 minus 32.24 squared over 32.24. Okay, and that would say that chi-squared is, and you get your chi-squared statistic, which is 3.22. That's fairly tiny chi-squared statistic. Okay, that seems like it's close to 0. So maybe your p-value will be bigger. Seems like it. Okay. Any case, so then we say the probability that chi-squared is greater or equals to 3.22 is, and you got this p-value from your calculator, and it's about 0.20. Okay, 0.020, and with your degrees of freedom being, now, what do I have? 3 categories and 2 columns. Okay, so I have 3 minus 1 times 2 minus 1, which is 2 times 1, which is 2. Okay, that's my degrees of freedom. And then I'm done. I can conclude, okay, since the p-value, which is 0.2, is greater than alpha, which is 0.05, we fail to reject the null hypothesis. Okay, so we say we don't have sufficient evidence to conclude what? That there's a difference. Okay, that there is a difference in party affiliation between the cell-only and landline populations. Between the cell-only and landline populations. Whoa, that's a mouthful. Okay. Yeah, don't just do calculator results. Yeah, don't just do this, please. Terrible. If you make any mistake, you're dead. Okay. Do some work. List your degrees of freedom. Do some work. Okay. All right. That's it, guys. Hope this helped.